The next-gen embedded Linux experiment now runs on a Beagleplay. So, in this video, I will show you how to build and run the image, go over the process I used to create the BSP, and if you want an easy way to build and customize images for a Beagleplay, or if you want to bring a new BSP to the Yo build system, this video may have some information that interests you. So, this is the console, serial console, and we'll log in. And let's just check the... So, that's running. Next, let's go over the process of how we build and flash the image for the Beagleplay. So, first thing we do is make sure Yo is up to date. With the Yo update command, let's also sync the repos, or the modules. Let's just make sure the modules are all up to date. And let's start Yo. So the first thing we're going to do is set the machine. So these are the machines we support so far. And we'll select the Beagleplay. And we'll also select the image, and we'll go for the development image. So these are already pre-built. If you want to build these yourself, you'll probably want to do this on an ARM system like a Raspberry Pi 5 or a Jetson development board or some reasonably powerful ARM system. I'm currently running on a Jetson, but if you want to, you can also build on QEMU on a x86 with QEMU user mode, but it's fairly slow. So, for it to build the kernel, you'll need a couple hours of build time. So these are already built. So the first thing we want to do is flash the dev image. So we'll put the SD card and a SD card reader on our develop machine. And we'll select development image, press F for flash, select the SD card. Now the Yo will display removable media. It tries to figure out which devices are removable, tries to protect your main disks and everything. And then it'll also save your selection. So notice that it selected Dev SDA because that's one I've used before. So go ahead and select yes. And now it's writing the image to the SD card. Okay, once the card is written, we will install the card into the Beagleplay. Now to boot the Beagleplay from the SD card, you can hold the user button down while you power it on or reset it. And what this does is it forces the entire boot path to use the SD card. Otherwise, it will boot from the internal eMMC, and you might be running an old bootloader on there or an image. So we want to be sure we're executing the entire boot path from the SD card that has our newly built binaries. So I'm going to go ahead and power it on now. So now if we jump over to the console, we'll see it starting up. So if we scroll back to the initial boot setups, we start off with various SPLs, and you'll see those were built yesterday. U-boot SPL, and then finally U-boot. So there's like 3 stages of bootloaders, and then finally the kernel. So the AM625 architecture is pretty interesting, and if you look at the boot chain, we have a ROM inside the chip that loads the first stage bootloader onto the 32-bit core. So there's like 4 A53 cores and one R5 core. So we first start off with this 32-bit R5 core, and then that hands off control to the A53s, and then finally loads U-boot and then the kernel image. So you can see this is fairly complex. A number of different binaries needed to be built and packaged for this to all work. And let's just go through some of the units for this. So if we look for U-boot, these are our two U-boot binaries. If we look at the oops. If we edit this one, notice we had to specify a new tool chain. So this is actually a 32-bit tool chain, I believe, that's used to build for this 32-bit. So by default, we build with a 64-bit ARM tool chain in an Alpine container. But in this case, we had to install this. Also notice there's a huge number of Python dependencies in these builds. And again, these all came directly from Alpine packages. I didn't have to build anything additional, but it did take a little bit of work to figure out all these dependencies. And I ran into a number of build issues and just had to keep adding these dependencies. So what Yo does is when it builds something, it actually creates a sysroot, installs the dependencies into the sysroot or hard links them. It's fast, and in that way, everything that's needed has to be explicitly defined. It can't accidentally leak something from another unit into this. And we actually we bubble wrap the build, and that creates a hard isolation so that the build can actually only see the dependencies that are specified. So anyway, that's an example of one of the units that we created. Here's the main U-boot unit. Again, we're just hitting edit or the E key on the unit, and it pops us into our editor so we can view the unit source code. Let's see what else. Let's just search on Beagleplay and just see if there's anything else in here. Yeah, that's about it. So how did I create this? I did it mostly in Claude Code. I just pointed Claude at the meta TI layer from Yocto, and I said create a machine support for a Beagleplay. And it got most of it with one shot. The only thing it didn't get right was there were a couple minor build issues that it straightened out quickly, but then the big thing was all the missing dependencies in the unit. And apparently with the TI build processes, there's quite a few Python tools used. So I had to go through cycles to do that. And it basically pulled in a bunch of Alpine community packages to provide all those dependencies. So why is this significant? One of the big bets with the Yo build system is that AI can help us create the BSPs or port them from other systems quickly. And this is a big bet, because if this doesn't work, then the whole project pretty much falls flat. So this is an important validation step, that we were able to take a fairly complex device with lots of bootloader stages, point it at an existing BSP from another system, and it was able to create a BSP in this build system fairly quickly and without a lot of effort. So yeah, this is really encouraging. I think the process is working well, and look forward to adding additional BSPs to the project. Let me know what you think. Thanks.